Dear host, dear friends, hello everyone. Today we would like to present our paper, A Narrow Gate Point, Driving Human-Robot Interaction from Work for Think Process. We will introduce our paper from these 5 parts: introduction, direct work, method, experiment, and conclusion. Human-robot interaction is a required method of information interaction in the age of intelligence. The new human-robot collaboration work model is based on this information interaction method. Human-robot interaction can be applied in various fields of life. For example, human-robot collaboration in the industry, intelligent education, intelligent services in family, intelligent medical care in the medical field, intelligent transportation, whereas really actually are all evolved from human-robot interaction support. The development of human-robot interaction technology also promotes the progress of human society so that human beings can enter the intelligent society first. Various human-robot interaction methods exist such as gesture-based human-robot interaction, voice-based human-robot interaction, touch-based human-robot interaction, and gate-based human-robot interaction. A mixture gesture-based, voice-based, touch-based are the most commonly used human-robot interaction methods. However, they also have some limitations. For example, gesture-based human-robot interaction rely heavily on human body movements and will not be able to complete the interaction when the creature body movements are limited. Voice-based interaction is seriously affected by the noise of interaction environment and requires the quiet environment to interview. Touch-based is a contact interaction models and connote the interactor which at a distance and the interaction contact through the touchpad, and also increase the risk of sprinting some distance. Therefore, the target gate-based interaction is game attention. Gate-based interaction reduces the dependence on the interaction environment and avoids indirect contact with the interactor through no contact interaction. However, most of existing gate-based interactions are done with the assistance of an eye tracking device, although the external web device have achieved good experimental results. The dramatically reduce the convenience of interaction and the physician of human-robot collaboration, and to improve the convenience of interaction and the physics of human-robot collaboration, we built a gate point-driven human-robot interaction framework without the existence of any external wearable device, just using RGB cameras as the video shows. First, we operate the distribution of interaction get points through the global view. Infer the get target from the get point distribution and the object position, and further driving the robot to grasp the target object. In this paper, we build a framework for get point-based interaction which only requires RGB cameras without assistance of external wearable device. We decide a feature to fill infinitely get points, report to a efficient location-based actually matching mode. In the get point-based HRI research, get point estimation is the first step in the interaction, and the use the estimated get points to drive the robot through the wise task in human-robot interaction. In the correct research, the methods of acquiring get points can divide into those that rely on external wearables and those that do not. Among the methods which external wearables, the main one is a use of eye tracking, where among the methods without external wearables, deep learning-based methods are the dominant ones. Modern-day approach incorporating get points in human-robot interactions will vitally. The completed tasks are also different, such as controlling the movement and grasping of the robot arm through gas interaction, controlling the robot for acceleration, giving the robot a navigation accurately. However, as mentioned above, the correct get-based interaction are done which external wearable device with framework for interaction which after the add of external wearable device is as follows. As shown in the picture, the global view merely sizes of object location distribution, opportunity and get point distribution, estimating object location distribution. Opportunity is used to obtain the position distribution of object. The get point distribution estimating is used to estimate the number of valid get points floating around each object. The get target resource and entirely matching use get points distribution information from the global view to infer the get target and find the target object in the local view through a matching algorithm. The object location distribution, obtaining and the moving and dropping are used in the local view. The object location distribution, obtaining has the same phase as the object location distribution obtaining model in the global view. The moving and dropping convert the pixel coordinates of the object in the local view into coordinates in the object coordinate system. In the future, we will describe the interaction process in detail. Step 1. In the global view, we use the object location distribution obtaining to get the distribution of objects. The flowchart is shown in the future. Step 2. We use get point distribution estimating to opposing the infrastructure get point distribution in the global view. The flowchart is shown in the figure. The corresponding port code is available in the paper. Step 3. In the local view, we use the object location distribution obtaining to get the distribution of objects. The process is the same as the first step. Step 4. The distribution of the HRI get points is used to infer the get target in the global view and match them with the objects in the local view by the entity matching algorithm to find the target in the local view. Before entity matching, you need to make sure that the object board position in the global view corresponds to the object board position in the local view as shown in the future. Step 5. Convert the coordinates of target object to the best coordinate system and HRI's moving and grabbing coordinates. This is described in more detail in our paper. Throughout the experiment, we used a workbench, collaboration board, the object to be grasped, a best robot which paired grappings, and the best robot had camera and the left hand camera and had as hardware device as shown in the figure. The best head camera is a global view camera, and the best left hand camera is local view camera. To thoroughly verify the partners of our framework, we set up experiment with different interaction distance, lightly and person. The figure shows that we set 3 interaction distance bands: near, medium, and far. We conducted experiment under natural daylight and electric light conditions at night. We invited 9 persons to help us with the experiment. 5 male, 4 female, 5 were my classes, and 4 were not, and they were of different heights and sizes. The table shows the results of our experiment under different conditions, where N, M, F denote near, medium, and far respectively. EL denote natural light and electric light respectively. The table shows that the success rate, the radiation gradually will the distance get farther, but different lightly does not affect our success. A more detailed analysis is present in our paper. In this work, a human-robot interaction framework uses only RGB cameras without the assistance of any external variables is built. In this framework, the robot uses only RGB camera to refer the target of the person gaze and grasp it. But the adaptive machine algorithm convert the target object from the global view to the local view to convert coordinates more structured, results in the long interaction time. In future work, we will focus on solving the problem and extending the framework to accommodate multiplayer human-robot interaction. Thanks.